Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to take what's called a distributed load and replace it with an equivalent single force vector. So first of all, let's take a look at what we're looking at over here. So we've got this load here, and this is what's referred to as a distributed load. It's kind of like the type of load you get if we had a big pile of sand actually in a geometry, something like this. That would give us a load that might look something like so. All right, and this number right here, this 3 kilonewton per meter, is referred to as what's called a load density. Now the first thing to notice is 3 kilonewton per meter. In order to turn that into a force, it has to be multiplied by some sort of distance. Right. So what I'm going to do is I'm going to try to calculate a pair of force vectors that I'm calling F1 and F2 that will replace this triangular load here on the left and this triangular load on the right. There's really 4 unknowns over here. We're looking for the value of F1 and then the value of F2 and then where they go on this beam, X1 and X2. Now I'm going to go ahead and do this example by what I call brute force, by direct calculation, and then I'm going to, in other videos, I'll show what I would call kind of shortcuts. Being that these are triangular load distributions, they can be handled quite easily without much math. But I'm going to go ahead and use the brute force method with a little bit of math. So first I'm going to focus on this triangular load. Now, what everyone needs to realize here is that the load density increases to the right. Right, so I'm going to let W here, that's a pretty common variable for load density, represent this function. And I can see that it's a linear function. And I can see that it goes through the point when x is equal to 3. Oh, and I should put a coordinate system in. I'm going to go ahead and put x, y. When x is equal to 3, the load is equal to 3. So this linear function basically is can be described by just W equals x. Because the slope is 1, if I take the point 3 at x equals 3, and then the other point I use is the load density is 0 when x equals 0, and you find the slope, you get 1. And then furthermore, I can just see by observation here that the intercept is 0. So W equals x is the equation of this line, and what it tells me is the load density anywhere I want. So for example, if I put an x equals 1 here, then right at this point here, the load density is 1 kilonewton per meter, and so forth. Now, what I'm trying to do is calculate a force. So the way we do that is we're going to break this load distribution up into little chunks here. So I'm going to imagine breaking this into a little rectangle here. And the width of this rectangle would be dx. The height of that rectangle is described by this function. And the area of this rectangle represents a force vector down on the beam. And I would call that a dF, because if I'm looking at an infinitely small piece, then the force associated with it also is infinitely small. Right? Now I can write myself an equation here. dF is equal to the load density at this location, which is described by x. And again, this is a number with units of kilonewton per meter, times this length here, dx. So what I've done is I've written myself an equation that tells me the force on any little piece of area here. Let me restate that. What I've done is I've written myself an equation that tells me the force applied to that little piece, and that force is equal to the weight density at that location times the width. So the area of this little rectangle gives the value of this force vector. The total force we can get then by adding these all up. And in mathematics here, the way we add here is through the integration process. Now, the total force then is going to be the integral over x. Now x is starting at 0 and ending at 3. This is equal, or this integrates to x squared over 2, evaluated 0 to 3. And that's going to be 9 halves, or 4.5. So 4.5 newtons is the value of F1. Now, I'd like to point something out here. Notice that the area of this triangle here, 1/2 3 times 3 is 4.5, and this is always true. The total force is found by the area bound under this curve. So in this example, although I set it up using a differential and integration, in future examples, I'll just take note that it's a triangular area. 1/2 base times height gives the magnitude of this force. All right, next, the other thing we got to do is figure out where that force is applied. Now, the net force for this triangular load needs to be equivalent, but also the net moment needs to be equivalent. So what I'm going to do is I'm going to write another equation calculating the moment about O. And that's going to equal the force at this location. And for now, I'm going to call it dF times this distance, which is x. So what I've done here is I've written an equation equating for the moment of this force about this point. That would be a differential moment because this force is a differential force, dF. Now what I'm going to do is go through and calculate a value. The total moment then created by this force distribution, we're going to have to add these all up. All right, so the dF in this example is x dx. And again, we're going to now multiply by x to create a moment, and this is going to be integrated from 0 to 3. Right. So this guy right here is going to equal, now this is x squared dx, that's going to integrate to x to the third over 3, evaluated from 0 to 3, which is 9. Now when I put units in this, Newton meter, because this thing was in newtons and this in meters. So I know that the net moment needs to be 9 Newton meter created by this distributive load about this point. Therefore, looking over here now, I'm going to deal with F1. F1 is at an unknown location, but the moment that it creates is equal to F1 times X1, or in this example here, let's see, 4.5 newtons times X1, and we don't know that, and we need that moment to equal 9 Newton meter about 0.0. And then we can solve this for x1, and we get 2 meters. So we know that this force here is applied at 2 meters from the left end, and we know that it's a 4.5 Newton force. Now, something I'd like to point out. You'll notice that 2 meters is 2/3 of the way from the end, or another way to think about that, 1/3 away from this corner. And I'm going to make another video on this, but it turns out anytime you have a triangular load, the load is equal to, or the force load is equal to the area of the triangle, which will be a 1/2 base times height, and then it's going to be applied 1/3 of the way from this corner, in this case 1/3 of the way to the left, or you could do 2/3 from the other corner, either case. Now, I've got the force and location for the first distributed load. We're going to take a look at now the second distributed load here, this guy. And I'm going to take a moment and get rid of this stuff here. And I think what I'm going to do is chat about a couple ways to do this. All right, so now we're going to focus on this load distribution. The idea here is we're going to break this up into little rectangles, the load. The area of that rectangle represents a force downward on the beam. Now again, that would be a differential force because the width of this rectangle I'm going to call dx. Therefore the area of the rectangle is infinitely small. Now, I think what I'll do here is just chat about what I know the answer to be, and then I'll talk about how to get it by direct integration. All right, this force 2 has to equal the area bound under this triangular piece, just like in the previous example. And that's going to equal, oops, do this in black, 1/2, 1.5 times 3. And I'm just going to talk about units out here. When you take 3 kilonewton per meter times 1.5 meters, you get kilonewtons. And I need to go back. That 4.5 was actually kilonewtons, not newtons. Kilonewtons. And the units on this guy, also kilonewtons. So this ends up being 1/2 1.5 times 3. That's 1.5 times 1.5. I think that's 2.25. 2.25 kilonewtons. All right, and then the next question is, where does it go? Well, I'm going to use that same rule, 2/3 from the corner, or I'm sorry, 1/3 from the corner. So this distance is 1.5. 1/3 of that would be 0.5. So this is 3 meters and another 0.5. X2 should work out to be 3.5 meters. 3 meters from here to here, and then another 0.5, and I'm getting that from 1/3 that distance. So that would put it at 3.5. Now I'm going to go ahead and go through the calculation here, though, using differentials and integration. Give me just a moment. All right. So now we have this load function here. And the first thing I'm going to do is I'm going to write a function in terms of this coordinate system, taking note that when x is equal to 3 meters, the load density is 3 kilonewton per meter. And when x is equal to 4.5 meters, the load density is 0. So this is a pair of points. The slope I can now get by taking the difference between these two. So I'm going to take 3 over 0. 3 kilonewton per meter minus 0 kilonewton per meter over 3 meter minus 4.5 meter, which ends up being 3 over, let's see, 3 kilonewton per meter over negative 1.5 meters, which is minus 2 kilonewton per meter. So now I know that this load density, the function for it, looks like minus 2x plus an intercept. I'm going to go ahead and find that now. I can use either of these 2 points. I know that when x is equal to 3 meters, the load density is 3 kilonewton per meter. Right? And I'm looking at my beam. If x is 3, then the load density above that's 3 kilonewton per meter. So I'm going to go ahead and I'm going to leave the units out just to make this a little easier. So this is our 3 kilonewton per meter minus 2 times x, which is 3 meters, plus my intercept. I'm just going to put b there for my intercept, just like y equals mx plus b. So that's a minus 6 added to the right. We get a 9 out of that. So what we know now is that the load density for this part of the curve is equal to minus 2x plus 9. And then the units come out to kilonewton per meter. All right. So now, calculating the net force. I need a little room, so I'm going to get rid of this. All right, so this force right here, dF, is equal to the load density at this location. That's this height of this rectangle, which is defined by this function, minus 2x plus 9. So again, this represents a number with units of kilonewton per meter times dx. The total force, F2, therefore, is going to be the integral of this expression, minus 2x plus 9 dx. Now, in this example, x is starting at 3 and ending up at 4.5. I should put NCU for note consistent units. All right. So minus 2x plus 9 is going to integrate to minus 2x squared over 2 plus 9x, and then that's evaluated from 3 to 4.5. I'm going to take a moment, just pause this and not let the video get longer while I calculate a value. Oh, and by the way, these would cancel. All right, folks, I'm back, and I went ahead and evaluated this expression at these two endpoints, and I got 2.25 kilonewtons, and I look right here, and that's the same as my projected value, so I'm happy about that. Next step is going to be the value for x2, and I think what I'm going to do to keep this video short is I probably will set this up, but maybe not finish it. This video is getting a little longer than I normally like. All right, so the idea here now is that the moment produced by this triangular load has to be the same in both pictures. So I'm going to write an equation for the moment on the left-hand side. Now the moment that this force produces about this point is calculated by taking this force So our dm is equal to the force dF times this distance x. This would be a differential moment because this is a differential force in my picture. The total moment then is therefore the integral from 3 to 1.5. Now dF, just like it was before, whoops, I seem to have erased it. I'm going to pause this and go look back and see what that was and come back to you folks. Sorry about that. Okay, I'm back. So that second load density was minus 2x plus 9. So we had the load density of minus 2x plus 9. That was good in this region. I just had to kind of go backwards in time with my system here and go look at what that was. All right, so that's our dF, minus 2x plus 9. Actually, the minus 2x plus 9 gives the load density. This thing has units of kilonewton per meter. To create a force, that has to be multiplied by dx. So this is now equal to dF times x. I'll go ahead and put this over here. All right, so this is now a force times a distance. It's now a moment. And now what I'm going to do here is just see if I can get this integrated. All right, so this term right here is minus 2x squared. That's going to integrate to minus 2x to the third over 3. This term is 9x. That's going to integrate to 9x squared over 2. Evaluate at the following limits, 3 and 1.5. Oops, I'm sorry. Should have been 3 and 4.5. If you were following that along in the video and you saw that mistake, I was just making sure you're paying attention. No, that was an honest oops. So again, the integral over here is from x equals 3 to x equals 4.5. I'm going to take a moment here and pause this again, get a numerical value here, and then we'll go ahead and see if we can figure out what x2 is. Hopefully we'll get 3.5 out of it. Hi folks, I'm back. Okay, so it took me a couple tries here to run that through a calculator and get a value that I was happy with. I ended up getting a value of about, oh, pardon me, I'll get rid of that, about 30.38 kilonewton meters. And now to figure out where force F2 is, what we're going to do is we're going to say, all right, this moment of 30.38 kilonewton meter has to be the same in both pictures. That's the moment produced by this triangular load about this point. Over here, that's going to equal this force, 2.25 kilonewtons, times the distance I have labeled as x2. Again, I'm pretending like I'm not sure where that's going to be. And when we take this whoops, I'm sorry. I have an incorrect number here. Not 30.38 kilonewtons. That was just the first part of this. By the time we evaluate this, what I got, let me write it down, is 30.38 minus 7.88. I'm sorry. Sorry again. 30.38 kilonewton meters was evaluating at the 4.5 minus, when we put in the bottom, I get 7.88 kilonewton meters. So numerically this ends up being, darn it, I did it again. Can't seem to even copy a number down right. Okay, 30.38 kilonewton meters is when we put the 4.5 in, minus when we put the 3 in, I get 22.5 kilonewton meters. The difference between them is 7.88 kilonewton meter. And now over here, when we take 7.88 kilonewton meter, which is the net moment created by the triangular load about this point, and set that equal to this force times the unknown distance x2, and then we solve for x2. So I'll go ahead and write 2.25 kilonewton meter times x2. And when we solve that for x2, I get 3.5 meters. All right, so anyway, sorry about the end there. Got a little bit messy at the end, but I think the gist of the video is okay. So as far as how do we handle distributed loads, all right, in general, how you handle them is you need this load function. In this case, it was a triangular load function, but it can be anything. It can be quadratic, or you'll probably see problems with sine waves or who knows what. But in the end, you typically need this load function. You break it into little pieces. So you look at a little rectangular piece of it. The area of this rectangle gives the force at that location. That will be a differential force because this is infinitely thin. You then integrate the, although I don't have it here, but you would integrate the load density. In this case, over here, it was x times dx would give the force, integrated from 0 to 3 to give the total force. Then you take that total force times an unknown distance, and you have to set that equal to the moment produced by the distributed load about that point. Right? And that's what this does. And the way you get the moment for the distributed load is you look at your little rectangle. The area of that rectangle will be the load density times dx. That's then multiplied by distance to make it a moment, and then integrated through the appropriate limits. Once you get a numerical value, right, in your picture, in this case on the right, your simplified picture, you can take the force you calculated before times x, set it equal to the moment found by integration. Now, there are several simple types of geometries that show up a lot in engineering type problems. One of them is a triangular load. Another very common one is a rectangular load density. And for a triangular load density, you just find the area of the triangle. That gives the value of the force. And then that force goes at what's called the centroid of the geometry. The centroid of the triangular geometry is 1/3 from the corner. So in this example, this triangle can be this triangular load can be considered to be a single force at 1/2 3 times 3 as far as its value, and then the location is 1/3 in from the corner here, which would be at x equals 2 meters, which is what we calculated before. So anyway, this video is plenty long. I think I'm going to end it there. I hope that it demonstrates how to handle distributed loads. Have a great day.